Welcome to today's lesson on terminal velocity. We'll begin today's lesson by developing our understanding of how an object accelerates due to gravitational force when dropped from a height. Next, we'll explore how air resistance, a type of frictional force, opposes the motion of the falling object as its speed increases. Finally, we'll learn about how the object eventually reaches a constant speed called terminal velocity when the forces of gravity and air resistance balance out. So far, we have explored the concepts of gravity, mass, and weight. You know how to relate mass and weight and understand how they connect to gravitational acceleration. Building on this understanding, we can now introduce the concept of terminal velocity. This lesson will advance our knowledge of forces and motion by explaining how different forces interact to influence the speed of a falling object. Let's get started. When an object is dropped from a height, it begins to fall due to the gravitational force acting upon it. Gravitational force is an attractive force that pulls objects towards the center of the Earth. Near the Earth's surface, and without the effects of air resistance, this force causes a constant acceleration known as gravitational acceleration, which is approximately 9.8 meters per second squared. This means that for each second an object is falling, its speed increases by about 9.8 meters per second. It's important to note that this constant acceleration happens only when no other forces, such as air resistance, are acting on the object. In real-world conditions, air resistance slows down objects differently based on their size, shape, and weight. For example, a feather and a rock will fall at very different rates in air due to differences in air resistance. However, in a vacuum, where there is no air resistance, gravitational acceleration is the same for all objects, regardless of their size or weight. This means that a rock and a feather dropped at the same time in a vacuum would fall at exactly the same speed and hit the ground together. To illustrate this, if you were to drop a ball in a vacuum, in the first second it would accelerate from 0 to 9.8 meters per second. In the second, it would accelerate from 9.8 meters per second to 19.6 meters per second, and this constant acceleration would continue as long as only gravitational force is acting on it. However, in the real world, we do not drop objects in a vacuum, so we must consider the effect of air resistance. Air resistance is a type of frictional force that opposes the motion of an object as it moves through the air. When the object starts falling, air resistance is relatively small because the object is moving slowly. But as the object's speed increases, the air resistance acting against it also increases. This increasing air resistance means that the net force acting on the object decreases over time, causing the rate of acceleration to decrease as well. Instead of continuously accelerating at 9.8 meters per second squared, the object begins to face a larger opposing force from the air. Eventually, the upward force of air resistance becomes equal to the downward force of gravity. When these two forces balance out, the net force acting on the object is 0. At this point, the object no longer accelerates and continues to fall at a constant speed. This constant speed is known as terminal velocity. Different objects have different terminal velocities depending on their shapes, sizes, and masses. This can be illustrated graphically. For example, a feather has a much lower terminal velocity compared to a rock because the feather has a larger surface area relative to its mass, leading to greater air resistance. In today's lesson, we delved into the concept of terminal velocity within the broader framework of forces and motion. We started by discussing gravitational force and acceleration, highlighting how objects accelerate at a constant rate of 9.8 meters per second squared near the Earth's surface when dropped. We then examined the role of air resistance, a frictional force that opposes the motion of falling objects and increases with speed, thereby reducing the net force and acceleration over time. Finally, we learnt that terminal velocity is achieved when the force of air resistance equals the gravitational force, resulting in a constant falling speed. This understanding helps explain why objects like feathers fall slower than rocks and has practical applications such as in parachute design. This lesson has deepened our comprehension of how gravitational and frictional forces interact to influence the motion of falling objects. Watch the rest of the GCSE physics course at Sophos Education.